Tame, symmetric, periodic 4 algebras, which I think, well, I think it may be about a third of all tame symmetric algebras. Another third is Bauer graph algebras, which are related to Karin Bauer's talk before. And so here is the other part. But anyway, this is a bit difficult to deal with because we don't really have tools. It's fairly bare-handed because, I mean, the Ausländerreitenquiver of such an algebra is just tubes of rank 1 or 2, so you cannot really do very much. Anyway, so instead, this is very elementary and down to earth. So we're looking at a simple periodic module of period 4 and see what we can say about it. So there is an exact sequence, and so on one end there is the simple, on the other hand is also the simple. In the middle you have projectives. So it starts with pi, and then you get all the projectives were labeled by arrows starting at I, and so you have ending at somewhere. And then you take all the arrows which end at I, and so you get another bunch of projectives. And so this is the general setup. And so how do I do that? How do I change my, right. Okay, so what are the maps here? So anyway, so this sequence is the most important one. So I'm saying a bit more about it. So you have a map D1, which maps some tuple of x's to sum of alpha nu, x nu. And so then this has a kernel, this map, and the kernel is omega squared of the simple module. So then since it's period 4, it doesn't go on very far. So the next kernel is omega 3, and it's isomorphic to omega inverse. And there's also a general description of that in terms of arrows. So this is quite general. And so how do I go to the next page? Okay, so I've added the sequence again because you have to remember the notation. So one thing you can say is if the algebra is tame, then you would know that there must be lots of paths of length 2 which occur in some relation, because otherwise the algebra wouldn't be tame, right? And so you can use that because you can show if there is some path of length 2 which occurs in some relation, then there must be an arrow from the end of beta to the start of alpha. So you have a triangle here. And this is actually quite elementary. You take your relation, so it's alpha beta plus alpha something, might be in the radical. So x should be in the radical. Sorry, I can't write this now because I can't. And then you might have some other stuff because there might be some other arrows. So you write this thing here as a tuple in the kernel of D1 here. And since this you have a beta here and something in the radical, then this is an arrow. And so this must be a generator. And since it's a generator, then the T of beta must occur as S of gamma for somewhere in this summand here. And so, so you have a triangle because this gamma must be composing with beta and ending up with alpha. So you get a triangle. So this is completely elementary in some ways, but of course you need to have a relation. And so if the quiver does not have so many arrows, then of course it is more complicated, and so you have to work harder. However, we have 10 minutes, so I probably have by now only 2 minutes or so. And so I'm not going to do anything complicated. Instead, it's very elementary now. So the next thing is even more elementary, I hope. Okay, so you have this exact sequence here. And so you have these 2 modules here. Okay, so now you can do linear algebra. So you have an exact sequence with an even number of terms. Then by the alternating something, you know that the dimension vector of these 2 things in the middle must be the same, right? So it's completely elementary. So these two things have the same dimension vector, right? Great. So now I go to the next page back. Right. So this you can use it sometimes, because here is our little lemma. So Q cannot have a subquiver which looks like that, and all the arrows from I to I are shown, because if this is the case, then this R plus, which describes the arrows starting at I, so that's this one here, is just Pj, and the R minus, which describes the arrows which end at I, are J and T. Right, but they should have the same dimension vector, and then, okay, the Pj appears twice, so this tells you that this Pt is 0, but of course that's not really possible because it's a non-zero projective module, so you have a contradiction. Right. So anyway, so we have some arguments like that, which are nice and easy, but of course, this is not really everything, which it's not quite enough. So one needs to do a bit more. And then, of course, you could ask, if we only have a very few arrows, what do you have some problems? And there should also be some algebra of finite type. And here is an algebra of finite type. So suppose you have arrow where no other arrows start at I and no other arrow start at J, ends at J, then you have your algebra of finite type. And that's also fairly elementary in some ways, if one finds it. So, okay, so with this assumption here, omega of the simple module is just generated by alpha, right? But also omega inverse of Sj is generated by alpha. So this tells me that omega of Si is isomorphic to omega inverse of Sj, and therefore you apply omega to that and you get omega squared Si is Sj. Well, that's a very strong thing, because yeah, so the Sj sits in the middle of the sequence here, and this R minus should be the projective cover. So this tells you that R minus must be Pj, right? But this tells you that there is only one arrow ending at I, and it starts at J. So this is therefore a fairly small quiver. So now if you can turn the things upside down, because you know also that omega squared of Sj is omega 4 of Si, which is Si, and you can use the same argument again. And so you get just a quiver with two vertices and two arrows between them. And actually, as it happens, just in the previous lecture, we have seen a quiver like that on the last slide. So it was the algebra A of Wang's talk. And we even got a presentation of that. And it was a Nakayama, finite type Nakayama algebra. So here's exactly what you get here, where you get the finite type algebras. And yeah, right. So that's probably about, how many minutes did I talk? It's probably about enough. And since I can't show your picture, and so I think I should probably stop here. I had one more picture, which unfortunately is on my iPad, so I can't show you. Okay, thanks very much then. Right.